What's up, everyone? This is LeetCode 98, validate binary search tree. So we've done this problem in Python. Now we're going to do it in C++. So we're given the root of a binary tree, and we have to determine if it's a valid binary search tree, also known as a BST. A valid BST is defined as the left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Don't get thrown off by the word key, right? It's just saying, like, when you're given the root node, right? Everything to the right of this root node should be greater than the value here, right? So nothing over here should be equal to 2. It has to be greater than 2. Because also it says less than and greater than, not less than and not less than or equal to or greater than or equal to. No, it doesn't say that. It says less than, greater than. So if you have nodes that are equal to each other, it would not be a valid BST, right? If this 3 was a 2, it would not be valid. If this 1 was a 2, it would not be valid, right? It has to be less than or greater than. That's it. Okay? And of course, that same like logic and reasoning regarding how the structure of the BST is, it applies to these nodes too, right? Not just the root node. So if these nodes here have also have left and right subtrees, the same rule has to apply, right? So for example, here obviously we'd have a problem. This 4 is not greater than this 5. But let's say it was greater than this 5, right? Whatever this number is here, the left subtree has to be less than this, and the right subtree would have to be less than whatever this is, right? So anyways, that's it pretty much. I'm just going to edit in my Python explanation that I did for this problem, because I think it's, actually think it's fine. There's not much I don't want to re-explain it, but I'll just edit that in, and then we'll go to the C++ implementation of this problem. So we're going to basically keep track of the boundaries of where we should be within when we're traversing this binary search tree, okay? So we start at the root node, okay? That's what we're given. And so we're here at this 2, right? And we don't know what our boundaries are, other than it should be less than, or it should be between negative infinity and infinity, okay? That's basically like our default values where we start, okay? Because again, it doesn't matter what the root node is. It's valid either way. But we need these boundaries here so that we can adjust them as we move somewhere, okay? So for example, we're at this 2. Now let's say we're going to traverse to the left right here, like if we're doing a DFS, right? We're going to start at this 2 and traverse to the left, okay? In which case, this node would change, right? Because now we're looking at node 1, okay? But we need to adjust the boundaries. But what boundaries would we adjust, the left or the right? I mean, think about it, right? When we're at this 1 here, right, we need to be between what? We need to be between negative infinity, right, and this 2 here. That makes sense, right? That's what a valid binary search tree is. Because we wouldn't ever want this node here to be greater than 2, right? Or I should say greater than or equal to 2, right? So the right node would change 2. I call it right. You can call it max also, like maximum or minimum, right? In fact, in the code, I'll just write it like that. But here we're just gonna call it left and right. So the way now when we're at this 1, right, we're gonna, and we updated these variables here, the boundaries. We're gonna say, is this 1 here? If it is less than or equal to the left, or right, or this 1 here is greater than or equal to 2. If either of those are true, we're going to return false, okay? And that should make sense, okay? Because we never want this 1 to be less than or equal to the minimum or greater than or equal to the maximum, okay? And then obviously we're going to check the 3. We never return false here, obviously, because just by looking at the picture, you can see it's a valid binary search tree, right? This 1 is less than this 2. This 3 is greater than this 2, right? So the answer here is true, right? And this is just example 1, by the way. Now here, right, we're at this 5, for example, right? We're going to have negative infinity here. We're going to have infinity here, right? We're going to go left, and we're going to adjust this would be 1, right? The right boundary would be 5, right? And of course, nothing problematic here, right? This 1 is between negative infinity and 5, right? So we're going to go back up, right? So we're here again, and now we're going to go to the right, okay? Now here's where we are going to run into issues, right? Because when we go right here, Okay, this node is going to change. We're at the 4 now. We need to update these variables here. These variables, okay? And so when we're at this 4 here, okay, what is going to change, the left or the right? Think about it, right? Well, we know for sure this 4 better be between infinity and what? And this 5 here, right? And not inclusive, right? So it can't be equal to the 5. So the left would change, right? So we're going to change this to a 5. So we're going to say, okay, is 4 less than or equal to 5? Is 4 greater than or equal to infinity? Okay? And again, these are ors, right? If either of those are true, we return false. So right here, is 4 greater than or equal to infinity? No, that's false, right? Is 4 less than or equal to 5? Actually, yes. So this would be true. We have an or statement here, right? So we actually, if either of those are true, our result should be return false, right? Like programmatically, that's how we would do it. If one of those are true, we're going to return false, okay? Now, technically, I know in like a logical or statement, technically you would return true. That's not what we're doing. The way I'm speaking about this is programmatically. If one of these is true, let's return false. That's basically what we're doing. And the reason I'm stating it like this is because this is how we're going to do it in code. This is how we're going to check whether we have a problem or not, okay? So if either of those are true, right, it means we have an error in, like, think of it like that, right? If either of these are true, it means we have an error in our binary search tree, in which case we just want to return false, right? Which makes sense, right? It's not a BST, right? When we're here, everything to the left should be less than this 5. When we're here, everything here should be greater than this 5. Well, look, this 4 is not greater than this 5. This 3 is not greater than this 5, right? So we have issues. So our final answer is we're going to have to return false. Okay, so we're going to do the C++ implementation, right? We're going to check the constraints here. We don't have any weird edge cases to handle because the minimum number of nodes in the tree is 1. Okay, so we're going to have to define a function, and we'll just call it full valid. I'm going to say tree node long minimum and long maximum. Okay, now before we even do that, let's just call this function. So we're going to say return valid, and we're again passing it the root node, right? And then we have the minimum and the maximum. And again, those are negative infinity and infinity. So we're going to set the negative infinity by doing limits long. Then we're going to set the minimum. Let me just copy this and do the same, but for x. Okay. Now here is we're going to have an edge case, whereas because we're doing this like a DFS, right, recursively. So if we are at a node here, it has no left and right subtree. So if we go to the left and then the right, we're going to get null. And in that case, just return true, right? If there's no child nodes from where we're at, it's fine. So we're going to say if node null, right? Just return true. Okay. Now here is where we're going to say if the node value is less than or equal to the max, or sorry, if it's greater than or equal to the maximum, that's when we have a problem, right? So that's where we would return false, because let's say we're at this 1, right? If this 1 is greater than this 5 or equal to it, we have a problem, right? Because it has to be strictly less than, right? Less than, not less than or equal to, but less than, right? So if it's greater than or equal to the maximum, we have a problem. Additionally, right, if node.val is less than or equal to the minimum, then we have a problem, right? Because when we're here, let's say at this 3, right? This 3, right? This 3 cannot be less than or equal to this 2 here, okay? So yeah, just like basically, this is the important part of the code. Make sure you understand that, okay? Just basically checking whether you're in the appropriate bounds. And if you're not, we're going to return false, okay? Now we're returning false here, but conversely, you could make sure, not to return false, but just to make sure that, you know, no.val is less than the maximum, or no.val is greater than the minimum, and then do something if that's the case. Otherwise, return false. Right? People structure their code differently for this problem depending on whose solution you look at, but this is just how I structured mine. So yeah. Now we're gonna have to recursively call this, right? So we're gonna say no.left, right? If we're moving to the left, right? What are we changing, right? What about our boundaries is gonna change? Well, the maximum would change, right? So the minimum, we're just gonna leave it the same, and the maximum, we're gonna set it to wherever we're coming from. So if we're at this 2, this would, and we're moving to the left, at this 1, the new maximum should be 2. Okay. Likewise, we have to do and, right? Because we have to check the right subtree as well. So we're gonna say right. And again, if we're moving to the right, the minimum has to change. So we're gonna say no.val, and the maximum will be the same. Okay. Oh, let me see. Oh, sorry. I'm stuck in my Pythonic ways. Man, my bad. I was confused for a second. So yeah, that's our code, right? It's really not too complicated to understand, I think. This video might be a slightly long, but I just wanted to make sure I go through the examples, right, by hand, so you understand what this algorithm is doing. I hope this helped though, and that it's useful, right? Yeah, the code's pretty short actually, so hope this is helpful. And I will see you in the next one. I'm gonna submit first. And it works, okay? I'll see you in the next one. Peace out.